This means that anything a designer can draw, the computer can make. A laser traces the designer's thoughts into a bath of liquid epoxy resin. Wherever the liquid is touched by the beam, it solidifies. Little by little, one thin cross-section at a time, three-dimensional parts are formed. And in a matter of hours, the finished object rises out of a solution bath. You can make almost anything you need with this. Spare parts on long space missions, for instance.
NASA's involved in rocket prototyping not just to reduce the cost for models used in wind tunnel or hot fire testing, but we're also involved in research to develop machines, perhaps one like this, to support the astronauts on the space station or during the exploration of other planets.
Rapid prototypers could be crucial on missions to Mars. A space dock could be the launch pad for a ship that could get there. When its engine's running, a nuclear rocket ship is highly radioactive. On Earth, this is dangerous, but space is full of radiation already, and a little extra from the ship would be like pouring a glass of water into the ocean. A nuclear engine, essentially a nuclear reactor, could drive a rocket twice as fast as a chemical engine and provide a safer ride, too.
To get to Mars and back, using current technology such as the chemical rocket engines on the space shuttle, will require 3 years. The reason for this is that it'll take you 6 months to get to Mars. If you spend a month or two exploring the planet, and then try to race back and catch to the Earth, it is revolved around the Sun. With a nuclear rocket, we can get to Mars in 3 months. Then we can spend a month or two in exploration, and then we can achieve speeds of up to 30,000 miles per hour, racing back and catching the Earth before it gets too far around the Sun. Thus, the total mission time, round trip, is about 9 months. And from the crew standpoint, being out in space, cut off from the Earth for only 9 months, is far, far safer than a 3-year mission. So in my opinion, nuclear propulsion is an enabling technology. I believe that within 10 years we can design, build, and test a nuclear rocket that will allow us to launch a manned mission to Mars. For any manned mission that goes beyond the moon, faster is better. On a 3-year mission, the crew would be exposed to a radiation dose that exceeds their allowable lifetime limit. Because of the performance of the nuclear rocket, not only can we reduce the trip time, we can actually put shielding around the module in the ship on the journey between Earth and Mars.
That's all right for Mars then, but what propulsion system could be used to reach the stars? For starships, it's antimatter. This, the equal and opposite of matter, can be made in enormous atomic accelerators by smashing normal atoms together.
I first became interested in space travel about 10 years ago. I had, before that, been doing experimental particle nuclear physics, thinking at odd moments about how we could use the results of that research to make spacecraft fly. The challenge for the next generation of rockets is to go into deep space. That is, to explore the outer planets, let's say starting with Mars, and then to go into interstellar travel. Chemical rockets simply do not contain enough energy per pound of fuel to enable those missions.
The amount of antimatter in a matchbox could replace a boxcar of traditional nuclear fuels for powering spacecraft of the distant future. But until recently, there wasn't any way of taking antimatter to your rocket.
It's a prototype instrument which we are just completing. It's designed to trap and hold 10 billion antiprotons for a period of up to 10 days. Our plans are to manufacture a much more substantial trap, but will handle up to 1,000 billion antiprotons That number is significant and will allow us to trigger microfusion reactions with antiprotons. And in turn, that would enable robust space missions. We're talking about very fast missions to Mars with a very substantial spacecraft delivering perhaps 100 metric tons to the surface of Mars with several astronauts in a very quick period of time, round trip 120 days.
So antimatter suspended by magnetic and electric forces in supercooled thermos bottles could be the fuel for massive space liners. Once a second, the antimatter would detonate an explosion like a tiny hydrogen bomb. For now, though, the only crafts using antimatter are those belonging to the Star Trek fleet, and even they have their limitations.
By my calculations, we're going to need 50 years to get to Alpha Centauri using nuclear power, and that will be even a great challenge. So if we want to bring the people back, that would be 100 years round trip, and that exceeds the lifespan of most people that I've known in my lifetime. On the other hand, if we want to leave them out there, why, that's something to think about.
Antimatter really offers pretty much the only option to do an Alpha Centauri type mission in the time frame of interest. You always have to trade distance and time. It's really a speed question. And then if you have more massive ship, it takes more energy to get your ship up to that speed. So antimatter, in my opinion, is the only thing that offers the potential, unless you're willing to invoke some kind of new physics.
Our universe has evolved over a long period of time, and there are mechanisms and forces that are responsible for that evolution. And the more we travel in space and look at these objects admittedly far away and study them, the more we'll know about our evolution and our origins. And that's why I'm an enthusiast for space exploration.
One whose ideas may seem a little primitive to us today. There were so many things they didn't realize. But that's not their fault. Somebody had to start somewhere. And anyway, the ambition to reach the heavens was the same. And if we're going to fulfill those ambitions still, we'll have to realize more things we don't now realize, or are only beginning to. According to the laws of physics known today, a space rocket ship can't pass that ultimate speed limit, the velocity of light. And the universe is so enormous that even light takes ages to travel from one part to another. But what about wormholes, time warps, other shortcuts through space? In a future age of breakthrough physics, these could be possibilities, perhaps. Who knows? We've discovered so much since the beginning of this century. Imagine how much more we have left to discover.